introduce Professor Hugh Possingham again, because probably maybe you forgot. But Professor Hugh Possingham, he has dedicated his life to conserving biodiversity. He told me to say that he's mainly a bird watcher since he was 10 years old. 10 years old, yeah. He's a professor at the University of Queensland. He was chief scientist of the Nature Conservancy. He was also ex-chief scientist of the Queensland government in Australia. He is an elected member of the US Academy of Science. He's also a member of the Australian Academy of Science. He has more than 750 publications. He's in many, many boards, more than 30, he said, at the moment. And he really likes birds. So, yeah.
Thanks, Maria. Thank you. Thank you for that. Oh, good. Thanks, my slides. Thanks, Barbara. Welcome, everybody. And particularly, I'd like to thank Maria and Barbara for organising our trip. So we're largely here to teach a course on decision science for conservation, and that'll be Monday and Tuesday and Wednesday next week. So we're teaching a course at Chilaway, Chilaway. And my background in that sense is very unusual. I was trained as a mathematician, but I love nature, and then I know a tiny amount of economics, not as much as Stefan, but this much economics. So I combine a little bit of maths and a little bit of ecology and a little bit of economics to help us make better conservation decisions. And of those 750 Web of Science papers, 600 are about decision science tools for conservation. One of our most successful tools that Jennifer and I have worked on a lot is called MarkSan. MarkSan builds protected area systems and has influenced the national park systems, the marine park systems, the land-based park systems in over 100 countries around the world. South Africa, United Kingdom, all through the United States, all the big non-government organisations, WWF, the Nature Conservancy, Conservation International, Wildlife Conservation Society, and even down to local municipalities use MarkSan to help them prioritise spatial plans. So there's lots of parts to decision science and conservation, and Jennifer gave a good example of how decision science can be used in something where you wouldn't think it could be used, choosing countries to do a debt conversion. I'm going to talk about decision science for monitoring and research. This is my least popular talk. Most people hate this talk. This talk should upset some of you. Is anybody upset already? Is anybody a bit upset? And really I'm asking the question, who here thinks they're a researcher? Who here does some form of research of some kind? Who's a researcher? Hopefully half of you are. Who thinks that monitoring is good? Do you think monitoring is good? Is that a good thing to do? Yeah. Sometimes, maybe, not always. So I'm going to challenge whether we should always be doing it, because if we talk to people in universities, if we talk to scientists and ecologists, the first thing they'll say is you should do more research and you need more data and you should do more monitoring, because if you don't do that, you can't make a decision. And often they're right. Often more data is always good. There's nothing bad about more data. Nothing bad about more data. But how much time and money should you spend on research? Because you could be spending that time and money on actually doing things. So who here thinks they're an applied scientist who actually delivers outcomes on the ground by doing things? Who's very applied? I'm a very applied scientist. Yeah. And then there's people who are very pure scientists, and that's fine as well, because we need all kinds of scientists. So that's what I'm going to talk about today. I'm going to give you some examples of the role of decision science in helping us decide how much monitoring is enough, how much research is enough. And I'm going to start with a story about puffins. So this is a flying penguin, if you like. I think in the northern hemisphere they were very surprised to find penguins, like Australia and Chile has penguins. You have 2 common penguins here. Australia has some penguins. New Zealand has lots of penguins. Their penguins fly. And puffins are one of the most iconic species. And much Europeans, the Scottish, the British, North Americans love puffins. They're one of the most iconic birds in the world, like a panda or a koala. I went to a conference about 15 years ago in Scotland, I think it was Aberdeen. Was it Aberdeen? St Andrews, somewhere there. About. Maybe it wasn't there, maybe it was there. And there were lots of talks about how they were going to develop a monitoring strategy to determine whether climate change was affecting puffins. So puffins tend to breed on little islands all around Scotland, and they were spending millions of pounds on designing a monitoring scheme to count the puffins to see, is climate change and global warming going to cause trouble for our puffins? So I listened to these talks. I was the plenary speaker at the conference. I listened to these talks over 2 days, and I to give my plenary talk at the end, and I said, why? I said, why? Why? What are you going to do? If climate change is causing the puffin food supply to decline and the puffins start disappearing from the islands, what are you going to do? Are you going to give the puffins a fridge, a refrigerator? Every puffin can get a fridge to sit by their burrow to keep them cool. Are you going to breed the fish that they eat and throw it into the ocean? There's a lot of ecology where people are studying the impact of climate change on species. A lot. Thousands of papers. And I say, why? Maybe in some cases you can move them. So anyway, I gave this talk and I talked about other things. And at the last night there was a big dinner, and my wife and I were sitting at the dinner. It was in a golf club. Nobody was talking to me. And then after a while they drank enough whiskey to come up and chat to me and said, Hugh, we're annoyed with you. We're angry because you're saying that all this science and all this very brilliant statistical analysis, power analysis, looking at type 2 errors, very clever analysis, you're saying it's useless. But we've decided it's not useless. And they said, if Scotland loses its puffins, then we need to tell Iceland and Greenland to look after their puffins. So that was the action. So to my view, research and monitoring has to lead to a change of action. So yes, they had an action. We'll tell the Icelanders and the Greenlanders that they need to look after their puffins. And I said, why not tell them now? We think our puffins are stuffed. You know, our puffins are disappearing. We really think that you should look after yours and we'll help you do that. So sometimes if the action costs nothing to do or almost nothing to do, you don't need science to do it, you just go and do it. There's even if there's just a small risk that the puffins are disappearing, write to Greenland, write to Iceland and tell them that they should look after the puffins. So they still were angry with me and they've never invited me back. There you go. So I ask these questions all the time. Now Chile, you've got whales going up and down the coast presumably. Is it humpback whales? Humpback whales. Do you count the whales? Do you count them a lot? So, and in Australia, the whales, we count them every year, the humpback whales. And do you know what? ever since we started killing whales, they've been increasing at 10% per year every year. It's a perfect exponential growth curve. And we keep counting them. And it costs them $2 or $3 million a year to count the whales. Why are we counting the whales? Why are you counting your whales? Are they going up? Does anybody know what's happening to the humpback whales? Assume they're going up. Ours are going up really quickly. $2 or $3 million a year. And I said, are you counting them so that you can open up your whaling industry again and start killing whales for skirts and oil? That's what you kill whales for, right? Of course, nobody in Australia is ever going to kill another whale. Nobody in Chile is ever going to kill another whale, are they? Why are you counting them? $2, $3 million a year of counting whales. And they said, well, the minister often is asked, how are the politicians are asked, how are the whales going? So they need to have an answer. Is that enough of a reason to spend $2 or $3 million counting whales? Okay, so I can give you lots and lots of examples of people doing research. Jennifer and I have a nice paper. A lot of wildlife biologists love to catch things, birds and mammals and seals, and they catch them and they tag them and they track them all over the place and say, look, this is where they go. And I say, why do you want to know that? Well, sometimes they have a good reason, but sometimes they don't know. They just say, we need to know where they go to conserve them. And then I continually also again say, why? So we have a long paper about that. So after a while I thought, well, there are reasons to monitor and do research, and I wanted to classify them so I could organise them in my head so that we did know why we were doing them. So for example, let's go some good reasons to, if you're doing a conservation intervention and you're, say, improving groundwater, getting farmers to use less groundwater, or you're doing some restoration and you're being given money to do that, then you need to monitor to see if it worked. You need to monitor to see if that's good. That's a good reason to monitor. In fisheries, often you have a quota and then people might be counting bycatch of dolphins and seabirds, and if they exceed the bycatch, the fishery stops. That's good monitoring, because the monitoring leads to an action. Monitoring leads to an action. Often we need to make decisions. We need to make decisions about interventions for species and ecosystems. So we need better models. So we need to build more science. We need to gather more data about where a species is to know how to protect it. If you have a rare and threatened species and you don't know anywhere where it is, then clearly you need to learn more about those things. Probably my favourite is this. This is what academics have been talking about for years, active adaptive management, and that is where you actually monitor interventions. So you act in different ways for the species in different places. It's active adaptive management, and you have to monitor that, and then you try and work out which intervention is the best intervention. Should I be putting up nest boxes? Should I be killing an invasive weed? Should I be changing the amount of water that goes down a stream? And then sometimes you just need pure science. Now this is, I'm not going to talk about this, pure science is good because you never know what's going to be useful. If you looked at, say, cryptology, the mathematics of the banking system, that was all pure mathematics and everybody thought it was a silly waste of time, number theory, and those people now have made us billions and billions of dollars, cryptology. So you never know. So it's not bad. It's just in the world of conservation, how much pure science can we do when we're probably going to lose half the species in the planet in the next 200 years? How much basic science can we do? And then sometimes people doing monitoring learn a lot, which is good. Sometimes the public just want to know. So this is the whale situation. The public just keep asking the question, how are the whales? And they pay the taxes, so they should have an answer. And then, of course, many times we monitor things, like a lot of the bird monitoring I'm a big eBird person. eBird's very popular in Chile. You have thousands of people entering eBird lists. That data can be analysed from citizen scientists, and you can see patterns in it. And sometimes those patterns, you get unexpected results. But I suppose what I wanted to do is make it really very clear there are outcomes from these things, but many people start monitoring, and they don't know which ones of these they're doing. So I suppose my first message is there's lots of reasons to do monitoring and research, but be very clear what's going to happen after you do it. Or what, in TN's, the Nature Conservancy, what is your theory of change? What is your theory of change? And then the second question, though, is if you can explain why you're doing the monitoring and research, how much money should you spend on the monitoring and research? And this is called value of information theory, because you could have a conservation budget. You could be working for World Wildlife Fund, and you've given some money to work on a fox or a goose or a swan. Do you want to spend all your money on research and monitoring, or do you want to spend some of your money acting on the ground? And that question can only be answered with value of information theory. And we have a number of, it's not a big field in conservation science yet. It actually helps you decide how much of your money you should spend on gathering knowledge. So I'm going to give you a generic example, a very generic example. Okay. So let's say we're looking after, does anybody here like plants, rare plants? Nobody? Yes, good. Okay, so I'll direct this to you. Let's say you're looking after a rare plant. Chile has, what, 1,000 species of endemic plants, many of which are rare and threatened. And you're looking at managing invasive weeds around that rare plant, and you've got a herbicide that you're going to use. And you've decided that this strategy, in controlling invasive species strategy, the benefit, that is how much it improves the viability of the plant, so your outcome is this plant going to persist for the next 100 years? You've done some modelling and you've worked out that the benefit depends on something you don't know much about. So in plants, it's often like a classic one would be seed dormancy. How long does a seed sit in the ground before it germinates? And that can be 2 years, 5 years, for some species it can be 20 years. Under what circumstances? So there's something you don't know. I don't know. And this strategy does better if seed dormancy is high, and it does worse if seed dormancy is low. So that's good. But at this point in time, if I've only got one thing I can do I need to know, I don't know what this parameter is. I think it's here, but it could be there and it could be there. I don't know what it is. It does affect my outcome. It does affect my outcome. But if I've only got one thing to do, what should I do? One thing. For many things, for many species, there's only one option on the table. Go and do it. Okay, so that's not very interesting. What's interesting, though, is often I might come up with another strategy, a different way of saving this species. I might have another kind of weed control mechanism. And to be honest, if that strategy is better than that strategy, for every unknown parameter of this, every value of this unknown parameter, I don't care about seed dormancy, do I? Because strategy B always delivers a better outcome than strategy A. Do I need to do science? Science is going to resolve this and make this smaller, and my uncertainty is going to contract. Do I need any science to decide what to do? No. So that's the most important thing I'm going to say. Scientists hate uncertainty, and they want to reduce it. And they say, this parameter, this thing affects your outcome. And I say, I don't care. I don't care because I want to save the species, and the best thing to do, it doesn't matter what that parameter is. So this is probably the most important thing where you can always ask anybody who says we need to do more studies of this threatened species or this ecosystem. You need to say, prove to me it will change what we do. Prove to me it will change what we do. If they can't prove it, don't give them any money. They can do it on their own time. Of course, it's much more interesting if strategy B is better. This is what we think the number is, and they're both about good. But if the parameter is high, strategy B is better. If the parameter low is low, sorry, strategy B is better. If the parameter is high, strategy A is better. So under this case, knowing if seed dormancy is high or low would change what I do. But also, what am I doing now? I'm saying the change in benefit would be tiny. Should I spend $1 million tightening up this distribution and find out I'm here or there, when the actual benefit from changing strategy is tiny? I could have put the $1 million into doing more of one of these. So you don't have to you have to prove that the science will change the strategy and the gains will outweigh the benefits of just spending all that monitoring and research money on doing more of the activity. Just plant more trees, kill more weeds, don't do any more science. And of course, there is one circumstance when the science does matter. Here, there's a huge difference in the benefit of the strategy. So I have to do the science. And the benefit of the science the science does more for conservation than doing more conservation. The science does more for the species than doing more management. How often do you see people prove this in conservation? Not often. They don't want to know about this graph. Okay, so when we start talking to people about an endangered species or an endangered ecosystem or protected areas or water management, we should always ask, they say, you need to understand the system more. You need more models, you need more data, you need more distribution data. The first thing you say is, do you actually even have any options? If you don't have any options, you don't need any more data. Then you ask the question, what's the chance the research and the monitoring will change what you do? And then if they say yes, then you say, is the change going to be big enough to make a real difference? Or is it just going to be a tiny change? Okay. And why don't we take that monitoring and research data and put it into actual doing management? So you can see why maybe scientists don't like this bit of the talk. Another way of thinking it then is some monitoring is always, and science is always, a little bit's good. The question then would be, how much do we need to do? How much would we need to do? So let's say you've been put in charge of a threatened species, or you've been put in charge of a wetland, and you've got a budget. You've got $200,000 a year. You could spend all your money on monitoring and research, or you could spend all your money on management, or you could spend half on each. What should you do? Well, it's clearly spending all your money on monitoring isn't a smart thing to do. So you've got to do some management. So let's say the good thing about spending more money on monitoring is we're going to assume that our management is better. So there's a relationship between knowledge and the efficiency of the management. So we're going to say scientists and monitoring delivers more efficient management. But the more money, the smarter you get and the better you manage, the amount of money to manage goes down. So if we multiply them together, all you have to do is multiply this by this, and you get that. That's the relationship between the monitoring, fraction of money you spend on monitoring, and your outcome. And this is the sweet spot. So this would say, if that was the relationship, the optimal budget on research and monitoring is 10%. So in theory, we could do this for any particular problem. I don't think it's rarely ever done. And in fact, it's funny when you talk to the we both work for Nature Conservancy. There's probably people here from different not-for-profit organisations, conservation organisations. You often ask the question, how much of our annual budget should we spend on monitoring and research? And what's the answer? I have no idea. It's not 100%, and it's probably not 0%, but what does this curve look like? What does that curve look like? And how can we understand what that curve is? Strangely enough, often we talk to most of these organisations like the Nature Conservancy, 10% of the staff were scientists. So probably 5 to 10% of our money was spent on science and research. Is that the right amount? If you talk to a big company like Coca-Cola, other places, they'll often be spending 10 to 20% of their money on research. A big chemical company, often spending, medical company, 10 to 20%, but some spend virtually nothing on research. Do we know what that is in conservation? Well, it all depends on the problem. I think I've said most of those things. And what is the time? Yes, good. Now I actually need to know the time. I'm monitoring now. Oh, I'm actually gathering data. Good. 12:16. Okay. Yeah, I won't go through that example because it gives me a headache. I'm going to give you another odd example, and it's all about type 1 and type 2 errors. Now, is anybody getting tremors and feeling sick? Because do you remember being taught about type 1 and type 2 errors in science? And the first time you heard it, you had no understanding, and about the 10th time you finally started to understand what they were talking about. So this is one of the most traumatic parts of statistics. So what is a type 1 error? Well, let me explain it with an example. So let's imagine we're in Australia and we're asking the question, does logging of forests, just cutting down forests, does it have an impact on koalas? Or you could ask the same question, does logging your Valdivian forest have an impact on one of my favourite birds that I've never seen, the Magellanic woodpecker? What's that in Chilean? What's a Magellanic woodpecker? What's its Chilean name? That's right. So does logging have an impact on this bird? So you could, if what we see in Australia, the forestry companies, they say, well, let's have a null hypothesis. And the null hypothesis is logging does not impact capitero. Is that the word? Capitero. I'm going to say woodpecker. Logging does not impact woodpeckers. That's what a good scientist does, right? A null hypothesis. Nothing's happening. So they go out and they set up a program and they monitor forests that aren't logged, and they monitor logged forests, and they get a bit of data. And what do? They say, well, the type 1 error has to be 5%. So what is a type 1 error? That's the chance you say logging is having an impact, but it really isn't. So that's an error, and we're going to make that 5%. The other kind of error you can make in statistics is that logging is having an impact. Cutting trees down is having an impact on woodpeckers, so it's having an impact, but in fact, so you say, no, get it right. This is why it gets confusing. Type 1 error is you reject the null hypothesis and say there is an impact when there wasn't really. A type 2 error is where you say there is no impact, we can't reject the null hypothesis, but in fact logging is impacting woodpeckers. What is the type 1 error is always set at 5%, isn't it? 5%. What's type 2 errors in most ecological studies? 50%. Sometimes it's 80%. So there's an enormous bias into not rejecting a null hypothesis. Enormous bias, because ecological field studies cost a lot of money. So if you look at that sort of thing, the first question you then say is, the whole process of setting a null hypothesis is fundamentally flawed, because we do these studies and we find that in fact logging hardly ever affects anything because we don't have enough data, and therefore we say logging is fine. Why not, in fact, why set type 1 errors at 5%? Who made that rule? Why is statistical significance 5%? And why are these numbers so much worse? So what we're doing is we're biasing it for not rejecting the null hypothesis. So we have written a paper, and other people have pointed this out. What we should really do is make these errors the same. At least, in fact. So you could really do a system, say, well, they should be both 30%. So you're equally likely to make the mistake of stopping the logging because it's not having an impact, that's a mistake, or not stopping the logging when it does have an impact. That's a mistake. There's two kinds of mistakes, and we should make them equal. But in fact, that's not even true either, because then the question is, what is the value to society from trees, and what's the value to society from woodpeckers? And maybe woodpeckers are more important than trees and wood. Maybe wood is more important than woodpeckers. So that we should actually value forestry, and we should value woodpeckers, and we should set the type 1, 2 and type 1 and 2 errors in proportion to the value of the mistakes we could make. In proportion to the values of the mistakes we can make. And nobody ever does that. So I suppose what I'm saying, if you're going to do monitoring and research, then be very careful about how you pick a null hypothesis, how you pick a null hypothesis, because in fact at least they should be equal. And furthermore, when we did a case study of this, which was on koalas and logging, the monitoring program to get the type 2 error low enough was so expensive, you may as well just pay out the loggers and not do the logging. So we would have had to spend $10, $20 million to do enough monitoring to prove logging affects koalas. Just pay the money to stop the loggers logging. Don't do the science. Stop the logging. Because one thing I've sort of noticed, if you're talking about woodpeckers and koalas, what do woodpeckers do? They sort of live on trees, right? And if you chop them down, the null hypothesis, in fact, is insanity. The null hypothesis is insanity. The chance that chopping trees down has no effect on woodpeckers doesn't exist. I mean, they clearly have an effect on woodpeckers. So one of our biggest problems, I suppose, is when we train our students in ecology and science, we train them in classical statistics, which is great for pure science. Pure science, good. You know, you want to be able to reject null hypotheses and progress the science forward. But for applied science, those statistical methods are highly flawed, and you're better to use Bayesian approaches, and you're better to include economics in your decision making. The best kinds of actual applied science is when you do the science, the management and the monitoring together, and that's called active adaptive management. We have some papers on it. I strongly recommend anybody who has ever read The Ecological Detective by Hilborn and Mangle talks to you about how do you combine gathering evidence, research and monitoring. It's probably the most important applied ecology book in the world. Hilborn and Mangle, The Ecological Detective. And that tells you how to do the combination of monitoring and action together and do proper active adaptive management, which we all talk about, we never really do. And it's basically a trade-off between getting outcomes now, but also monitoring to slowly adapt your management activities. And there's an optimal way of doing that. I won't go through all of these, but I might just pick a couple because we've talked about spatial planning. This is an example by Hedley Grantham from South Africa. We talked a bit about spatial planning and Marxan and where do you put protected areas. One thing that often people say is we need to know more about where all the species are. More and more and more about where all the species are. So we actually looked at, this is South Africa. This is an area in the Cape, the Fynbos, which has the most biodiverse flora in the entire planet. I think they have, 9,000 endemic plants in an area about the quarter of the size of Chile, or half the size of Chile, 9,000 endemic plants. And people kept saying, we're going to build a reserve system. When you build a reserve system, you look at the distribution of lots of species. There's hundreds of species of proteas. And they said, we need more and more data. They had 4,000 plots where they counted all the proteas. 4,000, and they had them distributed over the entire region, and they used that to build species distribution models. We found that, in fact, they already had more than enough data. And if they delayed making more reserves to wait for more data, they would lose habitat and lose more species than if they made the reserves with the limited data they had. Okay? So that's the other impact of science. If you say, we're not going to do actions on the ground until we know more, then you lose things while you're not acting. And in fact, they only needed 1,000 plots to make a very good decision. With 1,000 plots, their decision was 98% perfect. Knowing more and more and more was only going to move them slightly further along the curve of perfect actions. Anyway, we have a whole series of papers about how do you optimally monitor to deliver management outcomes. Again, most of the scientists will say, let's just get more data, because more data is always good. If it comes at the cost of money or time, so time is really important. If you delay a decision because you want more data, then that's bad for the environment. When does that often happen? So the government wants to, you're worried about a mine, or you're worried about logging activities, you're worried about development. What often happens is the scientists will say, I'm worried about this mine. I think there's problems here. I've detected heavy metals, there's sedimentation going on, it's affecting the marine environment. What has often happened is you as a scientist, the government says, well, I think we need more data. Here's $1 million. Spend 3 years doing more research. And we buy it. We say, yeah, I get $1 million. I'll do more research and I'll prove what I already know with even more accuracy. What should really happen is the mining company should stop and prove they're not doing any damage. And once they've proved they're not doing damage, then they can start again. Why do we have to prove they're doing damage? Which gets back to the type 1 and 2 errors. Okay, so I think I've said many of these things. Basic research is absolutely essential, but if you're working like we were for the Nature Conservancy or for government, then you can't afford to do it. It generally has to happen in universities. This question about how much monitoring and research you should do is a decision science problem that I don't think economists have really spent a lot of time looking at. And so we need more research on that. When we're taught statistics, we're taught about null hypotheses and type 1 and type 2 areas and a whole heap of statistical tests that are incredibly impossible to understand. That statistics is not that useful for applied scientists. It's not that useful for applied scientists. I have ignored a couple of things. For example, doing research on one problem, like the first example I said, let's save this threatened plant, there are 2 management activities. Doing research on one problem may actually give you knowledge for another problem. Okay, so I didn't account for that. So there are benefits for studying particular threatened plant species, because once you've done the study, that could be transferred to another threatened plant species. So the value of knowledge can often be more generic than the particular problem you're dealing with. One thing I haven't talked much about is sometimes research has a negative impact on species. So I know my friends Mick McCarthy and Kirsten Paris, they were looking at how people studied survivorship in frogs and lizards, herpetologists. And herpetologists often tag particularly frogs by clipping their fingers and toes. They chop them, the tip off. And you've got 20 of them, right? So I can come along, I can grab Barbara and I can take the top of that toe, the second toe on the right foot and the third finger on the left hand. Then I come back and I know whether I can find Barbara again because she's missing these 2 digits. And you can actually tag then thousands of individuals, because when you try and put markers on them with amphibians, they don't stay on and all these other things. What do you think that does you're studying mortality rates in rare and threatened. They found by analysing the data that for every digit you lost, your mortality went up 10% over the next year. I mean, you're a frog and a reptile, you've lost some digits, and you're going to get infected and get bacterial infections, and you're probably going to die. Well, a slightly higher chance of dying. So sometimes, let's be honest, you cannot study a rare and threatened species without having some negative impact. Some negative impact. Once you catch it, stresses it, all these things. So you've got to be really sure that your science is going to deliver a bigger positive outcome than the negative outcome you delivered. That's an even less popular talk for people who actually catch animals. And any movement, you know, to be honest, they've done studies, bird watchers going to a reserve impact the abundance of predators in those reserves, just watching birds, walking around. There's studies, repeated studies, particularly big predators hate people and their abundance disappears in the reserves. Not for every conservation problem. So I'll end with that. And I suppose all I want to do in this talk is implore you to ask the really difficult question. If you care about conservation, you care about delivering outcomes for nature, and then people say we need more monitoring and need more research, just simply say why. You know, and they need to give you some reason, and then they need to say that that research is going to deliver enough information to make a better outcome for what you're trying to do in the long run. So they have to deliver more than they're taking. Thank you very much. Happy to take questions.
Thank you, Hugh. We're going to take some questions from the public. We have a hand here who can translate himself. Él se puede traducir a sí mismo.
I can do it in British, Australian, or American accents.
Good.
No, so I will say the question in English and then in Spanish. So thanks, Hugh, for the presentation. It was great. I have a couple of colleagues that they won't be happy when I send the video to them, so they can watch the presentation. And for us, it's really useful. We have a project with Stefan in Patagonia, and we have dealt with some kind of these problems. Right. Because we are working in a marine protected area. Right. They don't have any information. They have to make decisions. A classical problem. And some scientists, they want more money to do monitoring. And we don't know exactly for what, and that's the big question. So any of these things are really useful for us to start some new conversation with the government and try to think which is the best way to go. So I have just one short question. It's important for us that maybe I can read the paper, but you're here now. So I like the approach to the value of information to evaluate when we need more data. Yeah. But sometimes we have a lot of uncertainty, so we don't have any information or really few information. Yeah. So really, how much information you need to do that kind of approach of value information?
Oh, yes, yeah. If you're really at rock bottom. I mean, yeah, so let's say you are just trying to conserve a species and you don't even know where it is, then, you know, yes, you need to find some individuals. I think, well, so yes, you need people in the field, and often they see things in the field about the species you need to. So I think early on, when there's almost no information, there's a lot of this going on. There's a lot of serendipity. And so there is somewhat, in some sense, there's no substitute for a human being being in a location where in an ecosystem that's under stress, or where a species is in trouble, spending time in that location. And they may be doing things that appear to be fairly pure, but they see things. They see things that are unexpected, particularly with species that are very cryptic or locations that are very remote. So, for example, with marine protected areas, I often say, you don't really need any data. You can do a couple of things. You can look at water temperature. You can look at chlorophyll A from satellites. You can look at depth, and you can get bottom type, and you can get 4 or 5 parameters, and you can just stratify a whole marine system on 4 or 5 parameters and say we'll build a reserve system. Now that really is very upsetting to a marine ecologist. I say, you mean you don't know where, you don't have any information about fish or shellfish, or you know nothing about this system, you're just purely taking remote data. So in those cases I would say build a reserve system of just 10% of all these different kinds of ecosystems based on this remote data, because then that's what you're saving the building blocks. So water, we know that depth is important for marine organisms. We know water temperature, we know chlorophyll A. These are really, get a bit of everything, all the different biophysical drivers of life, conserve a representative sample of them. Then over the next 5 or 10 years, send in the biologists, and they'll find things that the remote data didn't find, right? They'll find many things and they'll say, and then add on later. But don't allow it to stop you doing something at the start. I think that's my advice. It's sort of a bit of a version of adaptive management. It's not quite. The good thing about marine reserves is you can move their boundaries much more easily than terrestrial reserves. If you put in terrestrial reserves, you end up with fences and ownership issues, and somebody's logging and not logging. In the marine world, if you do have to change the boundaries 10 or 20 years later, they can be done reasonably. Well, it's difficult, but it's not impossible. So you can be more adaptive in marine protected areas, I think.
Yeah.
But I think it's really important just to get something done. When the government's saying build me a marine reserve system, the worst thing that could happen is all the ecologists saying, no, we need to collect data for 10 more years. And in that time, 20 salmon farms appear, and there's more fisheries, and there's other impacts from other systems, and you've just lost a lot of opportunities. Yeah.
Yeah. Thanks.
Para resumir, Rodrigo preguntó que él encontró que era muy útil la presentación para su trabajo aplicado en Patagonia con Stefan, donde están trabajando en áreas marinas protegidas, donde hay muy poquita información. Entonces preguntaba cuál es un poco el trade-off entre ir a buscar información con este tipo de aproximaciones. Entonces Hugh decía que una aproximación, por ejemplo, era estos mapas de percepción remota de hábitat, por ejemplo, para poder determinar, por ejemplo, el 10% de conservar cada uno de esos hábitats, y de esa manera determinar áreas marinas protegidas y no detener un proyecto de conservación por 10 años para ir a buscar los datos ecológicos más finos. No sé si sí, más o menos. Ahí. Mi nuevo trabajo será traductora. ¿Otra pregunta? Another question? ¿Otra pregunta? No sean tímidos.
Yeah, thank you. I really enjoyed the talk. Well, it's a comment and I want your thoughts on this. But one of the things that I think is really interesting is, yeah, you showed the value of information, ABCs, and I totally agree that when we don't need information, we can act, and let's act. What's interesting in terms of the value of information, though, is that probably all those lines are not linear lines.
Yeah.
They're all thresholds. And that, I think, is really interesting, because if we knew how close we were to thresholds, all our decisions sort of change. And I think that's something, at least from more of the economic side, we haven't really explored. You mentioned a little bit like how we value stuff, or the value of discount rates are sort of implicit there. But if we don't know how close or far we are from a threshold, that really can change things quite a lot. All I know about it a little bit is a bit on prospect theory and how close or far we are from being winners and losers makes our decisions as society now really flip. So I think that's a really nice scope there.
So what you're saying is, what I didn't do here is say what's enough. So this is the benefit, this might be the growth rate of the population. So this is the growth. What you really want to know is where is the population not growing?
Yeah.
And if that line is sort of here, somewhere in the middle there, then you want to be sure that what you're doing is pushing you above that threshold.
Exactly.
There's thresholds in ecology, and of course there's thresholds in social systems and economic systems, which we understand. At least in ecology we know if a mother has more babies that become mothers than herself, then the species should prosper. And socially, there's some maths around it. Population viability, life tables. With social systems, of course, exactly when a community is close to a threshold of persisting or not is highly uncertain. And so that's why I think what I would say is do things, and I think there's always value in some form of evaluation of interventions, even if they're very simple evaluations. So Madeline Bottrell was one of my students, a brilliant student who ended up working for Vulcan and Moore and all those companies. She evaluated 45, I think, conservation activities in Samoa. And she found out in the end only 3 had enough data to say anything. So in Samoa, lots of little projects. They usually lasted 2 to 5 years. After 10 years, only 3 of them even had any data, and none had enough data to say whether they'd worked or not. So that's sort of saying, in general, in small projects and small NGOs, we're just not doing enough evaluation at all. And if we are, we're not telling everybody what we've done, and then nobody can really learn from any of those examples. The money was spent, the trees were planted, something happened, but nobody really knows whether we delivered the outcome we want. So in some senses, evaluation is a better term. Evaluation is just monitoring, but it's sort of like, it's like an auditing. It's like that first thing. It's like an auditing of the books. You know, somebody gave me $500,000 to deliver an outcome. At some point at the end of the process, somebody should check whether that fox is increased in abundance, whether that rare plant is safe or not. And that usually doesn't happen. It's scary, very scary. That's right. So I'm giving such long answers. Maria has no hope. No hope.
You have to look at the YouTube. Someone has another question? I have a question. I have a question, Hugh. You were saying that the value of information analysis have not been used much in conservation science. So I wanted to ask you, like, if you can give some recommendations, or how can we better integrate this theory, this value information theory, to be more effectively used in conservation science to assess and determine expected benefits in
so there's some good papers.
Strategies.
There's some
I'm
good
going to
papers.
translate. So
they're good papers, but the problem is the value of information analysis. These papers all do them themselves, costing a lot of money. So what's the value of a value of information analysis? So what we need is shortcuts. We need simple rules of thumb to do a value of information quickly, and we don't actually even have that. So we don't have it. But I would say somebody wants to do some science on a conservation issue, just saying, tell me a story about how your science will change what I do. So there's got a verbal theory of change. And then try and work out some quick way around a table with half a dozen experts is how much of a difference is this a game changer? Is this going to save the species? Is that got a 50% chance of doing that? Then it's probably worth doing. But so I think you can if you think about value of information theory and you think about these 3 questions here, these 3 questions are the 3 questions. You can do it with smart people around a room. You know, realistically, are there multiple options? What's the chance the research will work, and what's the chance the research could actually change what we do because we'll find a better way of doing it? And then what's the chance that there will be a huge difference to the species or the ecosystem? And at least you've got to go. It's like asking 3 critical questions. Yeah. I think there was a question back there.
So I'm going to translate a little bit. Yo pregunté que vemos que esta teoría del valor de la información se ha usado muy poquito en en la ciencia de conservación, entonces le pregunté si había algunas recomendaciones que podríamos hacer para más efectivamente integrarlo y evaluar estrategias de conservación. Y me decía Hugh que tenía muchos papers donde han dado varias recomendaciones, va a quedar grabado así que los pueden revisar nuevamente, pero una buena opción, expert elicitation maybe, juntar a expertos y hacer algunas preguntas y tomar atención, okay, cuáles son las opciones que tenemos, lo que será acá. ¿Cuál es la probabilidad de que la investigación cambie nuestros resultados y el beneficio esperado de esas alternativas de manejo. ¿Tenemos otra pregunta? Another question?
Hello, Hugh.
Hi.
Thank you for your presentation. I have one question about the impact in conservation or restoration on any project related. This monitoring is about when we are working in the project on where we are establishing the basis to make decisions. But how because we need to know which is the impact of our actions or the conservation project. So we had to make another monitoring plan for that, create indicators, but my question is when we should stop. When we know that the species is safe or the ecosystem is better, when we are out of danger?
Yeah, that's a good question. That's another very difficult question. This is a paper by Helen Regan, I think from 2006, where we were trying to work out when do you know you've eradicated a pest? So you have an area or a country or a region and there's a pest, an invasive species. So we did all the maths about how after you think you've killed them all and you can't find any, how many years do you wait? How many years do you keep going back to check? Because some pests are cryptic, so they could have seeds in the seed bank or they could be difficult to find. So yes, that is possible to answer that question, but you need to do everything's how long you should keep monitoring and acting. It's actually, you have to work it out for every problem. We don't have a simple rule of thumb. Well, we sort of came up with a bit of rule of problem, that problem. This was an interesting one by Iadine Chades. This is a PNAS paper where, for example, we looked at tigers in Sumatra. So tigers are in decline in Sumatra, tigers are in decline in many places, and there are a couple of big national parks. And the question was, they could do 2 or 3 things. They could have poaching patrols, lots of people, or they could set up a big camera trap monitoring system, or they could do a bit of both. And it was interesting, what we found is even if, the question is, when would you stop the poaching patrols because you thought the tiger had gone extinct, which is sort of the reverse question to your question, is when do you save it? We found that even if you had not seen a tiger for 20 years, you would still have anti-poaching patrols because it was still useful to do it. So, and then after 20 years, then you'd invest in a lot of monitoring, and then you'd finally prove they're gone, and then you'd stop the anti-poaching patrols. So there's a lot of interesting counterintuitive results in these circumstances, and so we don't have a simple answer. Every problem is different, unfortunately, which makes things tough, right? Often, though, I can say in Australia, which, like Chile, has a lot of invasive species problems, when we're trying to wipe something out, an invasive species, we usually walk away too soon. So we think we've wiped it out, the funding goes away, nobody can see any, and then we stop looking and government says done, and then 5 years later we come back and suddenly there's 1,000 of them and it's worse than it ever was before. So usually we stop post-intervention evaluations too soon.
Thank you.